Hey everyone, and welcome to this video on properties of exponents. So let's get this party started. Alright, consider the following. 5 squared times 5 to the third. Obviously this is going to be a really large number, but what we're interested in is whether there's a simple way to express this number. Well, using the definition of exponents, we can write 5 to the second power as 5 times 5. And we can write 5 to the third power as 5 times 5 times 5. I mean, that's the definition of an exponent. And so we see when we rewrite 5 squared times 5 to the third using the definition of exponents, we end up with 5 5s for a grand total of 5 to the fifth power. Let's try another. How about negative 6 to the third power times negative 6 to the fifth power? Again, this is going to be an even bigger number than last time, but again, I think there's going to be a way to express this number in a nice, succinct, and user-friendly way. Alright, let's explore. Like the last time, we can write negative 6 to the third power as negative 6 times negative 6 times negative 6. And we can write negative 6 to the fifth power as negative 6 times negative 6 times negative 6 times negative 6 times negative 6. 5 times in total. And so, we see that when we rewrite these two exponential terms using the definition of an exponent, we end up with 8 negative 6's being multiplied by one another. And we know how to write that. That's just negative 6 to the 8th power. Let's try another example using variables this time. How about w squared times w to the fourth power? Again, w squared we can rewrite as w times w. And w to the fourth power, we can rewrite as w times w times w times w. What do we end up with? We end up with 6 w's for a grand total of w to the sixth power. Now let's see if we notice a pattern arising here. It appears to me that every time we multiply two numbers with the same base, we're simply adding the exponents. 5 to the second times 5 to the third was 5 to the fifth. Negative 6 to the third times negative 6 to the fifth, we got negative 6 to the eighth. And w to the second times w to the fourth, we got w to the sixth. And this makes good sense. For example, in our last example, when I see w to the second power, I immediately envision two w's being multiplied by one another. When I see w to the fourth power, I envision 4 more w's being multiplied by another. So of course it makes sense that you just add the exponents to find the product. Now, is this going to be true all the time? Now, no, we've discussed only situations in which both of the exponents are positive. Let's see if this is going to work with negative exponents as well. So for example, 7 to the fifth times 7 to the negative third. Now, if this pattern holds, in theory, all we need to do is add 5 and negative 3, and our product should be 7 to the second power. But we're not sure yet, so I'm going to keep that question mark there. Well, let's use the definition of exponents again. 7 to the fifth power, that's the same thing as 7 times 7 times 7 times 7 times 7. And 7 to the negative third power is the same thing as raising 1/7 to the third power. So 1/7 times 1/7 times 1/7. All right, well note, 7 times 1/7 equals 1. They cancel out, if you will. So I think that this 7 and this 1/7 will multiply to 1. This 7 and this 1/7 will multiply to 1. And this 7 and this 1/7 will multiply to 1. And what do we end up with? 2 remaining 7's for a grand total of 7 squared. All right, the property held that time. Let's get rid of this question mark. Let's try another example involving all negative exponents. For instance, 9 to the negative second times 9 to the negative fifth. All right, so if this property holds and all we have to do is add the exponents, we should just add negative 2 plus negative 5, and that gives us negative 7. So in theory, our product should be 9 to the negative 7th power. All right, let's find out though. Well, 9 to the negative second power is the same thing as 1/9 times 1/9. And 9 to the negative fifth power is the same thing as 1/9 times 1/9 times 1/9 times 1/9 times 1/9. All right, and it appears to me that we've got 7 1/9. So what I think we have is 1/9 to the 7th power. And note that this is the exact same thing as 9 to the negative 7th power. And so indeed, our property held again. And in general, for any real numbers a, m, and n, a to the m power times a to the n power will just equal a to the power of m plus n. That is, if you're multiplying two exponential expressions together having the same base, all you gotta do is add their exponents. And like we just said, it's really important that these bases are the same in order for us to be able to use this property. So for instance, if you had something like 2 to the 3rd power times 5 to the 4th power, there's no simplifying we can do here, right? Some students are under the false impression that you could write this as 10 to the 7th power, but that is absolutely not the case. Since these bases are not the same, there's nothing we can do other than leave it as it is. No way to make this any simpler. All right, now that we've discussed what happens when we multiply two exponential expressions together, what happens if we divide some? So for instance, 2 to the 5th power over 2 to the 3rd power. Well, if we just use the definition of exponents, 2 to the 5th power is the same as 2 times 2 times 2 times 2 times 2. And 2 to the 3rd power is 2 times 2 times 2. And now we've got this fraction with a whole bunch of 2's in our numerator and our denominator, and we can do some canceling out, if you will. I think this 2 and this 2 cancel out, this 2 and this 2 cancel out, this 2 and this 2 cancel out, and we are left with just 2 2's for a grand total of 2 to the 2nd power. All right, let's try another one. What about 5 to the 7th over 5 to the 4th? Let's use the exact same strategy. 5 to the 7th power is the same thing as 5 times 5 times 5 times 5 times 5 times 5 times 5. That's a whole lot of 5's. And 5 to the 4th power is 5 times 5 times 5 times 5. Again, I see a fraction with a whole lot of 5's in our numerator and our denominator. We can do some canceling to simplify this fraction. I think this 5 cancels out with this 5 with that 5, this 5 with the other 5, and this 5 with this 5. And we're left with 3 5's for a grand total of 5 to the 3rd power. And maybe you can already sense some pattern arising here. It certainly appears that whenever we divide two exponential expressions that have the same base, we've been simply subtracting our exponents. 2 to the 5th over 2 to the 3rd, 5 minus 3 is 2, we ended up with 2 to the 2nd. 5 to the 7th over 5 to the 4th, 7 minus 4 is 3, we ended up with 5 to the 3rd. And for each of these, this makes a lot of sense. We simply expand all our exponential statements, and we've got these fractions that we can simplify very easily. Well, is this always going to be the case? When we're dealing with all positive exponents, life is groovy. We can simply visualize all the factors multiplying by one another and simplify as we know how to. But when they're negative exponents, things might get a little trickier. So let's try this with some negative exponents, and also when the exponent in the denominator is larger than that of the numerator. Let's do one with variables too. So how about w to the 4th over w to the 9th? In theory, if this property holds, all we have to do is subtract 9 from 4, and we should end up with w to the negative 5th power. All right, let's see what happens. Well, w to the 4th is w times w times w times w. And w to the 9th is w multiplied by itself 9 times. All right, I think we're ready to do some simplifying. I think this w cancels out with that one, this w cancels out with that one, this w cancels out with that one, this w cancels out with that one. And we're left with a fraction where our numerator is just going to be 1 and our denominator will be w to the 5th power. Well, 1 over w to the 5th power is the exact same thing as w to the negative 5th power. And so it appears that our pattern has held so far, because if we just subtracted our exponents, 4 minus 9 is negative 5, and we ended up with w to the negative 5th power. All right, time to try some negative exponents. What about 4 to the 2nd over 4 to the negative 3rd? In theory, if all we have to do is subtract the exponents, all we need to do is 2 minus negative 3, which is 5. So in theory, we should end up with 4 to the 5th power. But let's go ahead and do this thoroughly and see what happens. Now I'll give you the heads up. We're actually going to use the property we just proved before to help us with this one. So what we're going to do is, first things first, just rewrite 4 to the negative third power. 4 to the negative third power is the same thing as 1 over 4 to the third. Now we've got 4 squared in our numerator divided by a fraction. We know how to divide by fractions. If you're going to divide by a fraction, that's the exact same thing as multiplying by that fraction's reciprocal, namely 4 to the third over 1. And 4 to the third over 1 is the same thing as 4 to the third. And 4 to the second times 4 to the third, we definitely know is going to end up being 4 to the fifth. And that is exactly what we would have suspected if we had subtracted 2 minus negative 3. That would have given us 5, and our answer was 4 to the fifth. So this property is still holding. One more time. What if both the numerator and denominator have negative exponents? As in, 6 to the negative second over 6 to the negative fourth. Now in theory, all we'd have to do is subtract negative 2 minus negative 4, which is the same thing as negative 2 plus 4, which is 2. So in theory, we should end up with 6 to the second power. But again, let's go ahead and do this one thoroughly and see what happens. First things first, let's just rewrite both of these as fractions so that we have positive exponents. All right, so we've got the fraction 1 over 6 squared divided by the fraction 1 over 6 to the fourth. This is no problem. We know how to divide fractions. If you're dividing by a fraction, instead, you're going to multiply by the reciprocal. And what do we end up with? We end up with 6 to the fourth over 6 squared. And I bet you already know what this is going to be. We don't even have to write it out. This is going to end up being 6 squared. And if we had just subtracted the exponents before, negative 2 minus negative 4 is the same thing as negative 2 plus 4, gives us 2. And our answer was 6 squared. The property holds all the time. And in general, for any real numbers, a, m, and n, a to the m over a to the n equals a to the m minus n. That is, if you're doing division with two exponential expressions having the same base, all you need to do is subtract those exponents. All right, now we're going to do 5 practice problems. What I'm going to have you do is do them one at a time, and then we'll walk through them, and we're going to investigate a pattern that's going to really help us take care of these very quickly and accurately in the future. And to simplify these means to please write these expressions without any negative exponents. And if our response demands a fraction, let's please write this as a single fraction in its simplest form. So let's start with d to the second over d to the negative third. Why don't you pause the video and give it a try. All right, 2 ways to go about this. The first is to just use our property. We know that if we're dividing these two and they have the exact same base, all we need to do is 2 minus negative 3, which is 5. So our answer is d to the fifth. But the other way is to actually go about rewriting that d to the negative third as 1 over d to the third. And of course, if we're going to divide by a fraction, that's the exact same thing as multiplying by its reciprocal, d to the third over 1. And we end up with d squared times d to the third all over 1, which is, of course, d to the fifth. But one thing I want to note is that this term with the negative exponent traveled from the denominator to the numerator, and its exponent became positive. All right, let's do another one. How about 2 to the negative fourth over 2 to the third? Why don't you pause the video and take care of it? All right, of course, there are 2 ways to go about doing this. You can just subtract the exponents. Negative 4 minus 3 is negative 7, so our answer is 2 to the negative 7, which you'd prefer to write without a negative exponent, so that's 1 over 2 to the 7th. Or you could use the definition of negative exponents and rewrite 2 to the negative fourth as 1 over 2 to the fourth, all over 2 to the third, which is the same thing as 1 over 2 to the fourth multiplied by the reciprocal of 2 to the third, namely 1 over 2 to the third. And we end up with a fraction, 1 over 2 to the fourth times 2 to the third, which is, of course, 1 over 2 to the seventh. But one more time, I want to point out that in our original problem, we had 2 to the negative fourth in our numerator, and as we made our way through, we ended up with a 2 to the positive fourth in our denominator. Very interesting. All right, let's do some more. All right, this one's going to be a little bit tougher. Again, why don't you pause the video and take care of it. All right, so when we're faced with a problem having different bases, we should note that none of the properties of exponents we've learned about are applicable unless the bases are the same. So we should concentrate on handling simplifying the exponents for bases that are the same. That is, in this case, for bases that are g and the bases that are k. So we've got two ways to do this. We can, of course, use the properties. Let's do the g's first. G to the negative second over g to the fifth. Well, we could just do negative 2 minus 5, which is negative 7. So part of our answer will be g to the negative 7th. What about the k's? K to the third over k to the negative first. 3 minus negative 1 is 4. So we'd have times k to the positive fourth. Of course, our eventual answer, we want to have no negative exponents at all. So we'd have to rewrite g to the negative 7th as 1 over g to the 7th times k to the fourth. And of course, we can turn that into one fraction, k to the fourth over g to the 7th. All groovy. There's another way we can do this though. We could use the definition of negative exponents to rewrite all of our terms with negative exponents as fractions. So for instance, and now we can do that actual multiplication and we'll end up with a fraction over a fraction. And we know how to divide fractions. We simply multiply the numerator by the reciprocal of the denominator. And it's no surprise that when we multiply these, we're going to end up with k to the fourth over g to the 7th. But what I want to point out again is note that in our original example, we had two terms with negative exponents. The g to the negative second turned into a g to the positive second, but it had migrated from the numerator to the denominator. The k to the negative first migrated from the denominator to the numerator and became a k to the positive first. It appears that when we're multiplying all of our terms in the numerator and denominator of a fraction, wherever we have a base with a negative exponent, that term simply moves from the numerator to the denominator, or denominator to the numerator, but this time with a positive exponent. All right, two more practice problems. Again, why don't you pause the video and take care of this one. All right, we're going to discuss three ways to go about simplifying this. The first is going right by the properties. Let's concentrate on the a's first. A to the third over a to the negative 7th. If we subtract those exponents, 3 minus negative 7 is 10, so we should have a to the 10th as part of our answer. And the b's, b to the negative second over b to the first. Negative 2 minus 1 is negative 3, so we should have a b to the negative third as part of our answer. Of course, we prefer to have no negative exponents at all, so we're going to rewrite b to the negative third as 1 over b to the third, and we're going to write all that as just one fraction, a to the 10th over b to the third. Fantastic. Two more ways to talk about this. What I like to do is see if that pattern that we've been noticing is going to hold in this case. And that pattern was, whenever we have a fraction with all these exponents and everything is just being multiplied by one another, wherever we have a negative exponent, we can switch where it is in the fraction from the numerator to denominator, or denominator to numerator, and make that exponent positive. So in theory, after we simplify this, we should be able to take a b to the negative second from up here and make a b to the positive second down there. And this a to the negative 7th in the denominator should become an a to the positive 7th in the numerator. So let's see what that would look like. That would look like a to the 7th times a to the third over b to the second times b. And if you multiply these together, we're absolutely going to end up with the exact same answer that we did using the properties. The third way to do it is to be really thorough and just use the definition of exponents and all of our knowledge about how to deal with fractions. And I'm going to kind of go through that a little bit quickly. And indeed, we end up with the exact same answer. And note that that little trick we used earlier seems to have been totally appropriate and totally worked. All right, last and most difficult practice problem. Why don't you pause the video and please simplify this. Okay, again, when we have all these different bases, it's best to concentrate one base at a time. So we'll do base 3, then we'll take care of base H, then we'll take care of base P. Now I'll be honest, I'm not really a big fan of going straight by the properties and just adding or subtracting the exponents, or whatever it may be. I like to use this trick that I've been talking about, in which, since we have a fraction, and all we've got going on is multiplication in the numerator and denominator, no addition, no subtraction, no anything else, I like to go ahead and rewrite this immediately, where all of the terms with negative exponents switch places from the numerator to denominator, or denominator to numerator, and then have positive exponents. And once you have positive exponents everywhere, everything is so groovy and a lot easier to visualize. So that's what I'm going to do first. And now that we've got positive exponents galore, this should be no problem. Dealing with the 3's, 3 to the second times 3 to the second, that's 3 to the fourth. Dealing with the h's, h to the fourth times h, that's h to the fifth. And dealing with the p's, p to the fifth over p to the third, I'm sure you know that that's p squared. And just that quickly, we have our simplified version of that pretty nasty original fraction. And that's the strategy that I would endorse for taking care of these difficult problems. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.